Okay, in this video we'll take a look at the repair work that I did on the amp, including rebuilding the board. We'll talk about the CL80 Inrush Current Limiter. We'll do some tests before and after installing it to see if it's a worthwhile mod. I'm going to save comparing this to the other one, the unrestored amplifier, for the next video. Okay, the new capacitor showed up today. I figured I'd show you guys how it tests on the LCR meter, since I'm not sure that anyone's shared the test results of one of these Authenticaps. So this is Authenticap, which is made by F&T Cap in Germany. It's rated 550 volts continuous and 600 volts surge, and it's got 4 sections in it, a 30 microfarad section and then 3 20 microfarad sections. So let's first hook it up to the half moon, which is the 30 microfarad section. And I got the LCR meter set to 120 Hertz. So it's reading 29 microfarads and 3 ohms of ESR. The next section is the square, which is 20 microfarads. It's testing 19.92 at 4.47 ESR. And triangle, 19.9 microfarads at 5 ohms of ESR. And the circle, 20.3 microfarads at 4.62 ohms of ESR. And just for comparison's sake, I'll try out 2 capacitors I would normally use if I was doing this discretely. This is a Rubicon HXW 500 volt 33 microfarads. See 28.3 microfarads at a little bit lower ESR, 1.8 ohms. And then I also have a 22 microfarad of the same Rubicon HXW. That's 19.45 and 2.89 ohms, so I'm pretty happy with the F&T. Alright, I removed the circuit board from one of the amps. We're going to go ahead and get this rebuilt. I'm going to address some of the things that I don't like about it. I'm going to get rid of these Amazon metal oxide resistors and put some proper metal films in there. They're probably fine, but I prefer to have resistors in anything that I work on that I can actually find a data sheet for. They don't really specify anything on these. They don't specify maximum voltage. They don't specify temperature coefficient. There's just nothing on them but the resistance value. I'm also going to replace these polystyrene capacitors. I don't like them in this sort of environment as far as the heat goes. These 2 resistors here get to over 200 degrees when the thing's running. And over here are the KT88 tubes. This one actually doesn't get quite as hot as these 2, but they're still hitting around 145, 150 degrees after the unit's only been running for 20 minutes or so. So I'm going to replace them with C0G ceramics. We want this thing to be completely bulletproof. We're going to replace the Russian paper and oil capacitor with a modern polypropylene. And we're going to replace these, which I assume are polypropylene. I can't find any information on this part number online. And plus the new capacitors will match the color of the 0.1 microfarad over here. And yeah, just take a look at the work. It doesn't look too bad on this side, but when you flip it over, it's just terrible. I mean, look at that. I don't know what type of flux this guy used. It doesn't look anything like the stuff I use, which is Kester 44 or 245. And he didn't cut any of the leads really, which is kind of weird. Or I guess he cut them, but he just left them really long. I don't like that at all. So, and here's the new board I reworked. I pulled grabbed the tube socket out of the other unit, and it just looks a whole lot better. All proper metal film resistors. I made sure to validate the voltage rating on them. One thing to note is carbon comp resistors. This thing mostly had half-watt carbon comp resistors, except for a couple positions, which it said were 1 watt or 2 watt on the schematic. Carbon comp half-watt resistors are rated to 500 volts. Metal film half-watt resistors are rated anywhere from 200 to 500 volts, so you got to be really careful when you're reading the data sheet. They make some really small metal film resistors nowadays. I forget what brand they are, but the series is called SFR20. And they're rated a half watt, but they're only rated at 200 volts. So These ones here especially are getting the full B plus voltage, 480 volts or so. So you need to make sure these were all rated to 500 volts. This 1.5 meg ohm resistor is actually a special high voltage one that I had to get because they didn't have any 1 watt, 1.5 meg resistors at DigiKey that met the voltage rating. So that's an actual high voltage one that's rated to several kilovolts, but it was still cheap. And yeah, I've got the C0G ceramics in there. This 750 picofarad was like $2 each, kind of pricey, but how much nicer that looks. And these are all 50 or 100 ppm metal film resistors. The backside, nice and clean, much better than this. So this board I'm going to have to rework, and we're going to put this back in the other unit. Okay, let's talk about the power cord situation. So we're going to be sticking with a 2-prong power cord. Some people might choose to install a 3-prong power cord and ground the chassis. Let's take a look at the original schematic. So we have a non-polarized line cord, and depending on how you plug it in, the hot would either go to the switch or to the fuse. And if you flip it around, vice versa. Nowadays, it's suggested to use a polarized line cord, which is standard on everything. So we're going to have our hot, and we're going to wire it to go to the fuse first, followed by the switch. And then we're going to test out a CL80 inrush current limiter to see if that helps with the voltage spike at power on during warm-up. The other thing that helps a little bit with, since it has some internal resistance, is dropping the AC line voltage slightly. As you recall from the schematic, the standard back when this thing was new in the 60s was 117 volts. Nowadays it's 120 volts, and there's an allowance above and below that the power company can deliver your power within. So I've heard of some people having up to 125 volts in their home. So this will help tame that a little bit. We'll see if it helps. If it doesn't, we'll leave it out. And then we're also going to be replacing this existing cord, which does not have a strain relief, with a new power cord. I buy these at DigiKey. They're 6-foot long polarized cords. It's a NEMA 1-15P plug, and they're 18 gauge, and they're nice and flexible. And we're also going to use these Heiko strain reliefs. The part number is 1114, and that fits the knockout in this chassis. That's what they look like. Alright, let's see if I can film installing the Heiko bushing. So I've got the new cord in the hole, no bushing yet. Here's the bushing. So we're going to put it like this, kind of fold it over, get it in there. I already soldered one of the wires in, so it should be roughly in place. So kind of pinched it a little. Now I've got the tool. This is the key. Of course, I need to open the tool up a little bit. There we go. So you squeeze the tool, push it in, release the tool. There we go. Perfect. Now you cannot tug on that cord at all. So you can see that mod here. Now I could have chose to use a terminal tie strip for the neutral, but I ended up wiring the neutral in line and covering it in 2 layers of heat shrink because there wasn't a good spot for a tie strip. The screws that hold the transformers in are, I think, number 8. They're too wide for the terminal strip to fit over them. I could have probably swapped one out for a smaller thread, but I don't want to. The other thing you'll notice is I redid the bias supply. It's a little cleaner now. We've got proper axial capacitors instead of the radials that weren't installed very neatly. I had to replace both of these terminal tie strips because the originals were so bad they just wouldn't take solder, which would perhaps explain why the last guy just stuck the leads through and tried soldering them together. And I also made sure to make really nice mechanical connections and everything before soldering it. My goal is always to, crimp the lead over so that it probably doesn't need any solder, but obviously you put the solder there. So I'm a lot happier with the way that came out. You'll see that the circuit board back here is much cleaner. Let me zoom in on it. Again, this is the brand new board, but I trimmed all of the leads and removed all of the flux. It just looks so much better. I replaced some of the wiring in here with 600 volt rated Teflon insulation, silver plated copper. There's a seller by the name of Apex Junior that I get that from, and it's a really reasonable price. Also replaced the resistors on the bottom side. They're all metal film now, including the dropping resistor here on the filter cap. This is the new Authentic Cap 3020-2020. We installed it correctly by twisting the leads, like I mentioned in the last video, with the special tool, although you can use a pair of pliers. Replaced the 18K bias resistor with another one. I don't know why he had like a 5 or 7 watt resistor in there, because it's not needed. Installed another 100 microfarad 100 volt axial cap here with the Teflon tubing on the leads. I also did the yellow sheet mod where we install the 1N 4007 diodes. I actually used UF 4007 diodes for everything, so for the bias supply and for the mod on the rectifier. It's supposed to help prevent arcing. All right, the other thing that I changed from the original design was, if you look on the drawing here, they have the grid stopper resistors connected between pins 6 and 5. Now pin 6 is unused on these tubes, so the way this is set up is that it just goes straight from the board into pin 5, so that left pin 6 free. So I used pin 6 as a tie point for the screen resistors that we added. There weren't any there before. They call them screen stability resistors. It's supposed to prevent arcing in your power tubes. They're quarter watt 100 ohm resistors, and they are installed from the screen tap on the output transformer to pin 4. So we actually have the resistor between pin 6 and 4, and then we bring the screen tap lead from the transformer over to pin 6. And the tube socket here has a connection from the feedback circuit, so that's actually connected at pin 6, so it's not affected by that 100 ohm resistor. That's pretty much it for the bottom of this. The only other thing that I'll note is that we left the wiring out that went to the preamp, because we're not going to be using the preamp. So there was originally the 6.3 filament supply that would come over here, and there was also a high voltage supply with that, I believe, 22K resistor. We just left it out altogether. This isn't a full-blown restoration. If I was really going for it, I would have probably removed all the wiring from the tube sockets, scrubbed them down, really cleaned them up, but I'm just helping a friend out. I'm not charging him any labor for this work, so it's cleaned up fairly well, but there's definitely additional room for improvement in the future if he chooses. Okay, so I'm going to try something new tonight. I've got a HP 6813A AC source. We're going to use that to measure the inrush current of the amplifier without the CL80 installed. So the cool thing about this is it lets you choose the phase angle that the sine wave is at when the power's turned on. So if we look at the help here, there's the section, the Inrush Current Test, and it talks about enter a turn-on phase angle for the start of the output. Changing the start angle will usually change the amount of inrush current applied to the unit under test. A start angle of about 70 degrees often provides the maximum inrush current to the device under test. So we're going to try this out. And ignore the fact that this is a Tektronix oscilloscope. The only reason I'm using it is because it's a Windows 2000 computer that has a GPIB interface on it. I tried installing this software from HP on a Windows 10 laptop, and it just doesn't work at all. So this was my best option for running it at the moment. So what we're going to do is, first you have to set the voltage to 0 volts and then turn the output on, because the inrush current test itself actually turns the voltage on and off. And it's going to run it for 3 seconds. So I'm going to plug the amplifier in. I've got it connected to an 8 ohm dummy load. Not that it matters for this short of a test. And this power switch on it is on. So what I'm going to do is I'm going to change this to 170 milliseconds of division. And we're going to run over to test, then click inrush current. I'll set the phase angle to 70 like it suggests for worst case. Then you click create transient. So basically when we're ready, we're going to hit start transient. And looking at the table here, there's 2 steps. So the first step is 0.36574 seconds, and that is to get it at the 70 degree phase angle. So if you put a different number in the phase angle dialog box that pops up, the step duration changes. And then the next step is 3 seconds. So the device will have power for 3 seconds. So let's go ahead and run that and get our measurement. Okay, so I'm going to close this. So there is the inrush current of a Dynaco MK3. If I lower the divisions here, this is what the current waveform is, the red waveform. So it's showing peak amperage is 7.2 amps, and then AC current 1 amp, 125 watts. This is 120 volts. And if we zoom out again, you can see that the current drops. So this scale is up to 1 second. So it looks like our 1 amp there is at the end. But it definitely starts hard, which is why I think it has a 3 amp slow blow fuse in it. So I am going to do another test now without this tool. We're just going to power this on and double check the B+ voltage and see what that spike looks like on turn on. Okay, unfortunately I lost the audio on the recording where I ran this test in real time, but here's the result. So here's the data showing the voltage at the output of the rectifier, so pin 8, upon power on, and this is without the CL80 inrush current limiter installed, so stock configuration. And we can see that it spiked at 531 volts momentarily before settling to around 515. Okay, before we install the inrush current limiter, I want to get a few more data points. So the multimeter is still connected to pin 8 of the rectifier at the moment, and we're reading 515 volts. I'm also curious to see what it reads on the other side of the choke, since the schematic shows 480 volts. So let's take a look at that. I'm going to move the probe. So we're seeing 507 volts at that point. And what I want to do is I want to lower the AC supply voltage to the amplifier to 117 volts, which is the original design, and measure those two voltages. Because the CL80 inrush current limiter that we're going to install, even when it's warm, it still has some resistance, and it's going to drop the line voltage, which is actually a good thing, because our standard line voltage is 120 volts in the United States nowadays, and it's allowed beyond 125, I believe. I think it might be something like 126. So anything we can do to knock that back down just a little bit to the original 120 definitely won't hurt anything. So I'm going to go ahead and move this probe back to the original location. And then I'm going to change the voltage on the AC power analyzer to 117. And we'll watch that drop. So we're seeing 500 volts directly off of the rectifier. And if I move that to the other side of the choke, it's measuring 494. And the specification on the schematic, as a reminder, is 480. So we're totally fine there. That won't be an issue at all. And here's a measurement from the AC power analyzer. I'm actually going to go ahead and hit measure here, and it's going to take a measurement of the output from the AC source. Show us the wattage, amperage, all that. So idle, this amplifier is pulling in about 1 amp, and it's 103 watts at 120 volts. Okay, so I installed the CL80 inrush current limiter. I installed a 2-position terminal tie strip here and routed the power line back down and over. I didn't want to cut the lead on the transformer, so I kind of zip tied it out of the way to keep it its full length, but I think that'll work out nicely. So let's get some new measurements. Okay, we're going to run that same inrush current test again. This is with the CL80 inrush current limiter. So 120 volts, 70-degree turn-on phase angle. Go ahead and hit start transient. Okay, that completed. All right. So we can see that our peak amperage went from 7.2 something to 2.13, and there's much less of a spike here at turn on. So look at the scale. The scale only goes up to 2.24 amps. So that made a huge difference. In fact, that means we could probably change the fuse to something slower, maybe even a 2.5 amp fast blow. So that might be something I send them home with. So let's go ahead and turn it back on and check the voltages off the rectifier. All right, so let's test it. Started logging. Output on at 120 volts. So we should see this climb up once the rectifier warms up. All right, and we spiked at 503. Let's give this a moment to warm up. And the other thing that I'll do, once it warms up, we'll put an AC voltmeter between the hot and the neutral to see what the line voltage dropped to after the CL80. So normal operations while it's warm. We can see that it's still climbing as the Inrush Current Limiter warms up to normal operating temperature. I'm going to move the probe over to the other position where we should see our normally 480 volts. We're seeing 494 there. So we're pretty much at where we were when I was simulating this test with 117 volts line. So I'm going to say this likely dropped the voltage to around 117. All right, I think that was a success. I'm going to stop now. Okay, and here's the graph from that test. So we see that we spike at 503.8 volts, and then it drops and it slowly climbs back up, but it never really exceeds 503 volts. Ignore the stuff on the right. That's from when I was moving the probe around. I forgot to stop the log. So I'm really happy with that. All right, I don't have a neutral exposed inside the chassis, so I don't have a good place to clip onto, so I'm going to slip this probe here into the socket and show you the AC voltage, and this is after the CL80 with the thing powered on. It's been on for about 5 minutes. So we're seeing 117.5 volts, which is great because we're at 120 coming out of the AC power source. Actually, let me show you. Let me move this to the other side here, and I'll show you that 120. There we are, well, 119.7. All right, well, I'm going to call it there for tonight. I wanted to keep these videos around 20 minutes, and I wanted to upload it today, so I'll save the performance tests for the next video where we actually hook it up to the signal analyzers, the audio analyzer, and things like that, and I'll talk to you soon. Thanks for watching.